Thank you so much for joining us today. My name is Natalie, and I am the Wohlhaupter Product Manager here at Allied Machine and Engineering. We've got a lot of great stuff prepared for you today, including 3 demos, as well as some really exciting information to share. With the Wohlhaupter product line, we have all types of boring tools, including high precision, digital boring, we have rough machining tools, and even large diameter tools for your applications up to 128 inches on diameter. Today, we're going to focus in on rough boring. So to start out, I'm going to talk a little bit about what we have to offer for the rough boring products. So first you have the twin cutter tool. The twin cutter tools are available in a cylindrical shank, as well as more commonly the Wohlhaupter MBS connection. The Wohlhaupter MBS connection allows you to adapt to any machine type. We have a wide variety of master shanks, including dual contact, cat shanks, HSK, and even lathe shanks. With our twin cutter style, it's a replaceable insert holder which mounts onto a serrated tool body. So typically you're going to see either an ISO 80-degree diamond insert or a Form 20 triangle insert. Some of the smaller sizes have a trigon insert, and we even have tangential inserts, which I'll get to describing a little bit more later on here. So the full diameter range of the twin cutter is about 3/4 inch diameter all the way up to 8 inches, or 19.5 to 205 millimeters. There's 2 different styles of twin cutter tools. There's same level cutting and there's height displaced cutting. So with same level cutting, you're going to use the identical insert holder on both sides. So they're going to be set to the exact same diameter. They're going to be set to the same height. And this allows you to be able to use the tool as double effective to increase your penetration rate and increase cycle time. So this is great when you have a situation where you don't have to remove a ton of material, but you really want to get through that bore as quickly as possible. With the height displaced option, you're going to have 2 different insert holders, and the inboard insert holder is going to lead the outboard holder by about 30 thou. So that allows you to offset the insert holders and then remove more material. So this is great when you know you have to remove a little bit more material. It does have the tool running as single effective, but it has its application as well. We also have chamfering tools within the rough boring offering. So these are available in 2 different styles. There's either the replaceable insert holder that mounts onto that same twin cutter serrated tool body. And there's also the solid body chamfering tools. So this has the MBS connection on the back, and it already has the milled pockets into the solid body. So typically this is going to have more than 2 flutes. So that'll allow you to have a quicker cycle time. But these are available in 15, 20, 30, and 45 degrees as a standard product. But if you need something outside of that, we can look into a custom solution and definitely get something for you. The 45-degree chamfering tools are capable of not only front chamfering, but also back chamfering in both the replaceable insert holder style as well as the solid body style. We also have grooving tools, both radial and axial grooving tools. The axial grooving tools, again, utilize that same exact serrated tool body as most of the other twin cutter tools. And they utilize a support block as well as a replaceable insert holder. So this gives you both a diameter adjustment as well as a height adjustment. What that does is it allows you to have a custom groove size, as well as eliminates any kind of an imperfection at the bottom surface of your groove. So you can perfect the height positioning of those inserts if you have 2 on either side. And then lastly, the radial grooving tools is the only twin cutter tool that is designated to the grooving alone. So the radial grooving tools are a solid body. There's no replaceable insert holder or anything just because of the way that those inserts mount into the tool body. But there are 2 indexes per insert. So you do have a little bit of indexability with those. And most of the axial grooving tools have 3 indexes per insert. So it's a triangle style with that grooving form on the front. We have a wide variety of insert grade options, coatings, different grooving sizes available as a standard product. So we definitely should be able to find something for your application within our standard product offering. Another option is reverse machining or back boring. We do have insert holders, same thing. They mount to that same serrated tool body. So it just mounts in the same way, but it's a similar style. It's just gonna do back boring. And these are also replaceable insert holders and inserts as well. So lastly, we get into the really cool stuff. Unfortunately, you're not gonna see any of the large diameter tools running today, just based off of the capabilities here in our lab. But the large diameter tools are capable of a range of about 8 inches all the way up to 128 inches, or 200 millimeters up to over 3 meters on diameter. So both the basic, eco, and flex alloy serrated slides are capable of twin cutter, chamfering, axial grooving, reverse machining, and even finish boring. So lots of options, even though you're not going to see any of that today. So we are going to run our first demo, and we're going to use a lot of different rough boring tools. So I'm going to talk about what you're going to see here before we actually go ahead and run it. The first tool that you're going to see is a same level twin bore. So as I explained earlier, these are both going to be set to the same diameter, and we're able to run this as double effective and increase our penetration rate. So it's going to bore out to about 2.1 inches finished diameter. Next, you're going to see the tangential inserts. So I'm going to switch over to the phone camera down here to show you what these guys look like. So this is a tangential insert, and it's not what you're used to seeing out of a boring insert. It's what we call a flat face cutting geometry. So it cuts here on the side of the insert. And here's how it kind of assembles into, into the insert holder. And you may not know by looking at it right away, but this actually does have a second index to it. So when you wear through this cutting edge, you can flip it in this way, and there you've got your second index. So this insert is great as far as a strength aspect. It's a very, very strong insert. It doesn't have much of a chip forming property to it, so it's great for materials like cast iron, anything where that chip formation isn't entirely critical or isn't an issue, but it's going to be very strong. You're going to get really great tool life out of this. So what we're going to do with the tangential cutters is we're going to do 2 operations and create a large counter bore on the top of our part. So you're going to see 2 different twin cutter bodies in action here, but it's going to do the same idea. And then here's the second tangential bore. So again, same principle. These are both going to be set as same level cutting. So they're going to be set to the same diameter. It's just going to create us a nice counter bore on the top of our part. Next, you're going to see an axial grooving tool. So this is going to create a groove right on the top of our counter bore. And it's going to have 2 different inserts. So this is also going to run as double effective. You're just going to see one groove created there with that tool. Next, we're going to have a chamfering tool. So as I said before, this is a 45-degree chamfering tool, so it's going to do both a top and a back chamfer. We're actually going to have this tool also finish bore the hole that we previously bored with the same level twin cutter. So it's perfectly fine that you bore with the chamfering tools. You just want to make sure that your penetration rate reflects the appropriate approach angle of the tool. So we're going to bore, and then we're going to interpolate on the back side and create a back chamfer, and then we're going to retract and do a top chamfer on the main bore, and then also a top chamfer or a little deburr edge break on the top of the counter bore. And then lastly, we're going to see a radial grooving tool. So this is gonna enter into the hole and then interpolate around and create 2 nice radial grooves in that main bore of our part. So I will go ahead and turn it over to Rob Brown, and he's gonna run the demos for us.
All right. Thanks, Natalie. For those of you who don't know me, my name is Rob Brown. I'm the engineering trainer here at Allied Machine and Engineering. And what we're going to be doing today is we're going to be running a piece of gray cast iron with the various tools that Natalie just told you about. We pick gray cast iron so that way we can show you that tangential cutter in action, and also This allows us to run it with just air going through the tool, so you can actually see what the tool's doing instead of having to splash coolant all over the place. So to tell you a little bit about the machine is a Haas VF3 30 horsepower vertical machining center. It does have coolant through spindle capabilities, but for this first application, obviously we're just going to be running shop air, so it's going to be at about 90 psi of shop air. We're going to be running a piece of gray cast iron. It's roughly about 200 Bernal in hardness. And we're going to start off by doing the pre-drilled hole with our revolution drill. We're going to have it set to 1.875" diameter. It's going to run at 650 surface feet a minute and 5 thou per rev, which in metric is 198 meters per minute and 0.13 millimeters per revolution. So, Dave, if you're about ready to go back there, let's go ahead and run the rev drill and get it started. And then as it goes through the different various operations, I'll tell you what it's going to do. So once again, we're running the rev drill first, 650 feet, 5 thou per rev. Because with the boring tool, we got to put in a pre-existing hole. So that's what we're creating here. Okay. So now we're going to swap out to that Wohlhaupter twin cutter that Natalie was talking about just a minute ago. And we're going to be running it at 600 surface feet and 12 thou per rev, because since it's a twin cutter, we can do that. That turns into 183 meters per minute and 0.25 millimeters per rev. So now we're going to switch that out, and we should be coming in with the tangential cutter to put a little recess in the top of the part, and it's going to run at 600 surface feet and 10 thou per rev, which is 183 meters a minute. 0.25 per revolution. Okay, now we come out with a larger twin cutter. It's going to run the same speed and feed, 183 and 0.25 or 610. And we've now created the recess that we want to do. So now we're going to come in with that axial groover and put an axial groove in the top of the workpiece. So it's just going to come down and kiss that. The axial groover is running at 500 surface feet a minute and 4 thou per rev, which is 152 meters a minute and 0.1 millimeters per revolution. So that's that one. So now we're going to come in with that chamfering tool. And the first thing we're going to do is we're going to create the bottom chamfer, I believe. Oh, we're going to do the bore on it, then we're going to do the bottom chamfer once it gets through. So the top and bottom chamfer is going to run, it looks like 600 surface feet and 4 thou per rev for this one, which is 183 meters per minute, 0.1 millimeters per revolution. And whenever it's done with that, it's going to switch it up when it goes to do the circle interpolation to do the chamfer at the bottom and the top of the hole. It's going to be running at 800 surface feet a minute and 10 thou per rev, which is 244 meters per minute, 0.25 millimeters per revolution. So once it gets all the way through the part, now it's going to go do its circle interpolation. Okay, and whenever it's done with that, it's going to come up top. It's going to do a circle interpolation at the top of the hole. And then it's going to finish off by doing a circle interpolation of that recess up at the top to break the edge on in. So there it goes, and once again it's running at 800 surface feet a minute, 10 thousandths per revolution, which is 244 meters a minute, 0.25 millimeters per revolution. And whenever it's done, which is just about there, it'll be time to swap out for our last tool in this application. So now the last tool we're going to bring in is Radial Groover. The radial grooving tool is going to run at 600 surface feet and 6 thou per rev, which equates to 183 meters per minute, 0.15 millimeters per revolution. Okay, so now it's going to go down, it's going to circle interpolate that radial groove, and it's going to create two of those. So it'll create one at the top, then it'll go down a little bit and create the other one. So there's the first groove. Now it's going to go down and create the second groove. And then whenever that's done, we'll have Dave take the part out of the machine and we'll show it to you underneath the camera here so you can see what the part looks like when we're all done. So we're just about there. So basically we just took that from basically a raw blank into a tool that's been bored, recessed, has a couple of different, has both an axial and a radial groove in the tool or in the workpiece. Right behind you, Dave. So let's take a look at it. Thank you, sir. So we'll come over and we'll show you what we got here. Okay. So what we did first is we did the revolution drill to go and drill the hole and created that pre-drilled hole. Then we came in with the roughing tool, opened this up to a rough finish diameter, and we swapped that out. Whenever we brought in the chamfering tool, it created the finish bore here. It also came and did the chamfer at the bottom of the hole. Came up, put a chamfer at the top of the hole here, put another chamfer running around the crease here. Here's our axial groove, and then lastly we had that radial groover come in and create 2 radial grooves. So you can see there's one here and one here, and created this entire workpiece in what was that, about 4 minutes or so, something in that neighborhood. So it went relatively quickly. So that's some of the basic rough boring tools that we have. So we're going to have Natalie come on back in here and talk to us about the VolCut product, and we're going to run a couple of demos for that too.
Yeah, thank you, Rob. So the VolCut product is somewhat new to the Wohlhaupter product line. If you're familiar with our currently existing opening drill product line, this is essentially the exact same tool. The only difference is that it's capable of doing much larger diameters. So this can even be used on the basic Eco and Flex Aluline serrated slides to bore up to 128 inches on diameter. So that's where we really see that this tool excels, is at those much larger diameters. And it's also capable of going as small as around 2.5 inches as well. So this is really meant for high material removal within one operation. So if you have an application where you just need to really hog out a whole lot of material, this is a really great product line. The tool performs best when you have optimal clearance because contrary to the opening drill, this serrated tool bodies, they don't have flutes. So you just want to make sure that you have plenty of clearance on the backside to evacuate chips out, because you don't want to be recutting, especially in a deeper hole application. You don't want to have any induced chatter or any issues there. So this tool actually uses the same inserts as well as the opening drill. So we have a couple of different grades, coatings, and geometries available. It uses those same opening drill inserts. So we have a couple demos prepared for you on this. We don't have any of the really large aluminum slide demos prepared for you, but we do have a couple. So I will turn it over to Rob again here, and then he's going to get our demos going.
All right, so coming back to me again. All right, so let's talk for a second about what we're going to do with the VolCut. The first application we have for the VolCut product is running in a piece of 4150 alloy steel that's 28 to 32 Rockwell. We have it set to a 4.5 inch diameter. It's going to be running at 600 surface feet a minute, 5 thou per rev, which is about 183 meters a minute, 0.13 millimeters per revolution. Now, what I have to tell you is our Haas VF3 does not have enough power to run a part that big. So what we have is actually a video of it running on our Monarch Machining Center, which is over in our R&D lab, because it has a larger capacity than what we can do with the Haas. So we're going to show you that video, and then whenever that's done, we're actually going to run a smaller VolCut that will run in this machine to show you how it works there, okay? So to kind of give you some information about the machine that's over there, it's a Monarch VMC Vertical Machining Center. It's about a 30 horse machine with a 10,000 RPM spindle. They have the coolant set at 500 PSI for this application. And whenever it goes to roll the video, I believe the hole's already there, the pre-existing hole, and we're going to open it up. What was the pre-existing hole size? Do you remember? We're going to call it 2 inches then. I don't really remember what size it was. Actually, I'm going to show you whenever this is done. We actually have the actual parts that we ran. We're going to show you a video of it running. And then whenever we cut back to live here, I'll show you how it did, and then we'll actually run a smaller VolCut here. So let's go ahead and run that video. We can kind of talk through it as we go. So you can see there's that pre-existing hole in there. Once again, the VolCut's going to run 600 surface feet a minute, 5 thou per rev, which is about 183 meters per minute and 0.13 millimeters per revolution. Okay, so as Natalie said, this tool is kind of developed to remove a large amount of material at once. So we're taking out about 2 inches of material off the diameter of the workpiece. So that's removing a lot of material all at once. So what we want to do with the VolCut product is you're going to go and it's going to substitute several rough boring passes by being able to remove a lot of material all at once. So as we're going through this, you can kind of see, there's not a lot to see here because of the coolant, but there it is, it's done. So we're going to switch back here, and I have a couple of pieces that I can show you. Let me get this one out of the way, we'll bring this one over. So if you want to go to that overhead, Kyle, let's take a look. This was the part that you just saw running. Kind of get it centered here so you can see it a little bit better. So you can see the quality. It has a very minimal amount of chatter. The surface finish actually came out really quite good on this. And this is a 4.5 inch diameter cut that we put in it. This is a 6-inch diameter piece of 4150 that's 28 to 32 Rockwell. So let's take a look at it as a through hole so you can see what that looks like. Okay, on the back side, you can see there's a little bit of an exit burr. Let me kind of tilt it up so you can see it there a little bit. So it does create a little bit of an exit burr because remember, since this is a single effective cutter, it is going to go and push that slug out the bottom of the part. But once again, surface finish repeated. It looks really quite nice there. You can see that. And then here's the exit disc that was created whenever the part drilled through. So you can see when we're looking at the quality of this, what we don't see is a lot of like clock face chatter on here or anything like that, which tells us that this tool ran nice and stable whenever it was doing its cut because there's very little chatter in the exit disc as it was created. Okay, so now that we've showed you that, let's talk about what we're going to do here. So for the last demo that we're going to be running today, we're going to run a smaller diameter VolCut. This one is going to be set to a diameter of, looks like 3.25 inch diameter is what size it's going to be. Is that right, Dave? All right, just make sure I got my numbers right. What we're going to be doing this in is instead of running it in another piece of 4150, we want to show you the versatility of this tool. So we're going to run it in some 304 stainless steel. That's about roughly 150 Bernal in hardness. So we're going to cut a 3.25 inch diameter hole. We're going 1 3/4 inches deep, running 600 surface feet per minute, which once again is about 183 meters per minute, 5.5 thou per rev feed rate, which is 0.14 millimeters per revolution. And we're going to have to do the pre-hole for this. The pre-drill for it, I believe, is a revolution drill that's going to come in. Oh, there you go. It's a 38 millimeter Vortex. It's going to go and create the pre-drilled hole. I got my applications mixed up there. It's Friday. I have no excuse. But here we go. So we're going to run the Vortex first, drill the pre-hole, and then we're going to come in with that VolCut set to 3.25 inch diameter and open it up, and then we'll show you the workpiece and the chips whenever we're done. So Dave, if you're ready, let's go ahead and go. Okay, so once again, we're coming in with the Vortex tool first, and I want to say it's running about 605. Does that sound about right? 605.5. Okay, so it's going to be running the same speed as the VolCut tool. Okay, so here we go with the Vortex. This is drilling the pre-existing hole because since the Vortex or VolCut is not a center cutting tool, we got to have a pre-established hole in there. And there are some calculations that you're going to have to do to figure out which is going to be the correct pre-existing hole diameter to figure out what the minimum is that you need to remove. Okay, so now we're going to come in with that VolCut, and once again we've got it set to 3.25 inch diameter. And what you'll notice whenever they bring the tool out is what you're going to see is the VolCut set towards the wider side of the diameter range for this. Once again, we want to make sure that we have area for that chip clearance so the chips can get out, because unlike an opening drill or really any other drill that we're going to present to you, it's not going to have flutes to exhaust that chip, so we've got to make sure there's area for that chip to come out of the hole. You ready, Dave? Let's do this. So here we go. Okay. So once again, we're going to run at 600 surface feet a minute, 5.5 thou per rev, which is 182 meters per minute, 0.14 millimeters per revolution, going about 1 3/4 inches deep. So we're not going to drill all the way through the workpiece, so that way you can see what's going on whenever it comes out. We'll take a look at the chips that get collected, and then we'll also take a look at the workpiece itself to see the quality of the workpiece. Okay, so we'll let Dave gather up some chips for me. Let me grab a napkin here to put it on. Alrighty, that'll work, Chief. Thank you. So while he's getting the part out of the machine, I can show you the chips that it created. That's what we have here. So taking a look at what we got, once again, 304 stainless steel. Let me get this kind of shifted over here so you kind of center it a little bit better. This is 304 stainless steel, about 160 Bernal in hardness. So the chip form that we get from it is pretty good, okay? Not perfect, but once again, usually when you're talking about 300 series stainless, what you're looking for there is not necessarily a perfect chip as much as a chip that you can manage. It isn't going to be a white bird's nest or something like that. Get wrapped around a tool body, those kind of fun things. So those chips came out pretty good. So let's take a look at the workpiece itself. And here's what we got. So you can see here was our pre-existing hole. Once again, it was a 38 millimeter diameter, which is roughly about 1.5 inch diameter pre-existing hole. This is what the VolCut did. And you can see the surface finish on it. It is a little bit rough, but once again, the idea with the VolCut tool is not that you're going to produce finishes and tolerances with it, that you're going to come in and use your finishing tool to create the tolerance that you want to have and also the surface finish that you need to have. The design intent with that VolCut product is basically to get rid of a lot of material quickly. That's really what the trade secret is with that. So that's what you get with the VolCut tool. So Natalie, if you want to come on in here and you have any closing comments or anything you want to say to everybody before we take off.
Yeah.
Why don't you turn your mic on?
Yeah, sorry about that. Help if you can hear what I'm saying.
There you go.
Lastly, I just want to thank everyone for joining us today. Thank you, Rob. Thank you, Dave, for running the demos for us. If you have any questions about more Wohlhaupter rough boring tools, visit alliedmachine.com/roughboring or reach out to your local field sales engineer or our application engineering team, and we will answer all your questions and get more information for you. So thanks again for being here and have a great day.
Thanks. See ya.